Good morning, everyone. So today we are starting chapter 6, and as you know that we are done with chapter 5, so now we are on chapter 6, and the title is Structure Analysis. So what are we going to cover in chapter 6? Let's have a look. So we are going to talk about simple trusses. We are going to talk about method of joints. We'll do zero force members, and we'll cover method of sections. So this is all what we are covering in chapter 6. So let's talk about trusses. So what is a truss? All right. So you must have seen the several different kinds of trusses, right, in the real world. On the right side in this picture, you can see there's a truss which is supporting this bridge, right? So it's a highway bridge, and over some kind of river or canal or lake, and this truss is supporting this bridge, right? So there are many other uses of these important structural members, which are called trusses, right? So now let's go ahead and see some more applications of trusses. Trusses are also used to support the roofs, as you can see in this picture. On the left side of the slide, this truss is holding or supporting the roof of this building, right? Okay, what else? For a given truss geometry and load, we need to determine the forces in the truss members. Now, why do we need to find the forces in truss members, right? That's a good question. That why do we need to find the forces in the members of the trusses, right? Because we have talked about mechanics, we have talked about strength of every material, right? So every material has its own strength. Some material is weak, some material is strong. They have their own strength, right? So the member of truss are also made of some material. They have some strength. They have some compressive strength. They have some tensile strength, right? So now we need to find the forces coming onto that members so that we can make sure that the forces which are coming onto that member of the truss, they are not exceeding the tensile strength or compressive strength, right? So that these members should not fail, right? So that's the purpose of finding out the forces coming onto these members. Okay. Now, for a given load, we can design the trusses geometry to minimize cost, right? So as you know that we can design any kind of truss, right? Because mostly they have triangular members, and sometimes they have other kind of members, and so we can design the truss based on the given load, and you can have any kind of geometry, right? So in that way, we can minimize the cost coming on to our structure, right? Okay, so that's another thing about the trusses. Okay. Now, some other uses of trusses. Trusses are also used in a variety of structures like cranes, frames of aircraft, or the space station, right? So these on the left side in this figure, this picture, you can see a crane using some kind of trusses, right? Okay, so that's another example of the application of trusses. We can also design a lightweight structure satisfying load, safety, and cost specifications with the use of trusses, right? With the use of truss structures. As you can see on the left side, left bottom picture, so this lightweight structure, and we have used different geometry of truss over here in this system, right? So all these are different applications of trusses being used for various purposes, for various structures, for various uses. Okay. Now, section 6.1 of your book, we will talk about simple trusses. Now, what is a simple truss, right? So let's talk about simple truss. So on the left side, in the top picture, you can see there's a truss which is supporting the roof, right? And it has some supports underneath, right, at four ends. Now, on the right side, in the top picture, you have the free body diagram of this truss, right? The same truss. Now, a truss is a structure composed of slender members jointed together at their endpoints. We all know that. Right? So, now, if a truss along with it, the imposed load lies in a single plane, as shown in this picture at the top, it is called a planar truss, right? So the free body, if you look at the free body diagram at the top right side, so this truss is in single plane, right? Let's say XY plane, right? So, and the applied loads, the external loads are also in XY plane, right? So there's no three-dimensional loading on this truss. So that's how we can say that this is a planar truss, because that's the condition which needs to be fulfilled to say that this is a planar truss. Okay. Now, this was one terminology, which was planar truss. Now, another terminology is a simple truss. So a simple truss is a planar truss which begins with a triangular element and can be expanded by adding two members and a joint. So essentially, we start with one triangle element and we add other triangular elements to make the truss bigger. So that's a simple truss. Now, on the left side, left bottom, you can see a picture where we have this truss ABC, right, which has three members, AB, BC, and CA, with two supports at A and C, right? So now this is a triangular element, right? And this is a simple truss and a planar truss, right? So if you add member BD and member AD, so you are adding two members and one joint, which is joint D, right? So you're adding these two members and one joint to the existing triangular element. So that's how we get this simple truss, right? So if you keep adding two members and a joint, it will remain a simple truss, right? Okay, so that's the that was the definition of simple truss and planar truss, and how do we make simple truss. Now let's talk about the relation between the number of members and number of joints. So let's say that number of members is capital M and number of joints is capital J. So this equation, if you see, M equals 2J minus 3. So this equation gives you the number of members for any simple truss. So let's take an example of this truss, this ACBDA, right? So this is a truss. Now, how many joints are there? So we have one joint, we have two joints, we have three joints, we have four joints. So we have four joints. So now how many members should be there? M equals 2 times 4, 2 times 4 minus 3, right? Because J equals 4. So what do we get? Okay, so we were finding out the number of members. So number of members in this case will be m equals 2 times, because there are 4 joints, or j equals 4. So 2 times 4 minus 3 is equal to 5, right? So how many members do we have? We have 1, 2, 3, 4, 5. So that's how it works. For any planar truss, for any simple truss, we can use this equation to find number of joints or number of members, right? Okay. Now next is force analysis of a truss. Now why do we need force analysis? We already discussed about it, right? We need to make sure that the member is safe, right? And the whole truss is safe. So when designing the members and joints for a truss, it is necessary to determine the forces in each truss member. Now, 2 assumptions are made for this force analysis, right? Force analysis is to determine the force, the internal forces in all the members of the truss. That is what is called force analysis. Okay? So to do the force analysis, we make 2 assumptions. What are those assumptions? All loads are applied at the joints, right? So that's the first thing. The weight of the truss members is often neglected, as the weight is usually small as compared to the forces supported by the members, right? So that is one assumption. The second assumption is the members are joined together by smooth pins, right? So there's no friction, and we take them as 2 force members, right? So with these 2 assumptions, the member act as 2 force members. They are loaded in either tension or compression, right? So as you can see here, this member is in tension, this member is in compression. And we use big T for tension and big C for compression, right? So these are the assumptions which we make to do the force analysis of a truss, right? Okay. Now, there are 2 methods which we are going to cover to do the force analysis of the truss. First one is the method of joints, and the second one is method of sections. So first, let's go over method of joints. So what is method of joints? How do we use method of joints? This is section 6.2 of your book. So let's go over it. Okay. So let's say that we have this triangular truss with 3 joints and 3 members. A, B, C is the triangular truss, right? And we have 500 newtons force on the top joint at point B, right? Okay. Now, to solve for the forces in truss members, the equilibrium of a joint is considered. So we take a joint and we analyze that joint to find the forces in truss members. How? We just apply the equations of equilibrium, right? But it's really important to understand how we take that joint and why this joint, why not the other joint, right? So let's see some other things. Let's go through some other things. So all forces acting at the joint are shown in a free body diagram, right? So we make a free body diagram of that joint. This includes all external forces, including support reactions, right? As well as the forces acting in the members, right? Or the member forces or internal forces in the members. So all these forces, the external forces, support reactions, and the member forces, we show on the free body diagram. And then we apply equations of equilibrium, sigma fx equals to 0 or sigma fy equals to 0 to solve for the unknown forces acting at that joint, right? Okay, so let's say we are solving for joint B here, this joint. So we just draw this joint. It's already drawn on this right side, but let's draw it again. right? So let's say this is your joint B, okay? Now, what forces are acting on this joint, right? So there is one tension force, this is 500 newtons. Why tension? Because this is pulling the joint, right? Is applying tension to the joint. So this is a tensile force, right? Now, what are the other forces? There's no other external force. There's no other support reaction at joint B, right? But there are two members, this one, which is BC, or this one, which is AB, which are joined at joint B, right? So we will have two forces, two member forces, which we need to include in this free body diagram, right? So let's say this and this. So this is FBC and this is FBA, right? So this was the joint, this is the external force, this is the member force, this is also the member force. Now, to assume the member forces at any joint, we can simply take tension in all the member forces, right? Now, FBC, if you look at FBC, this arrow is pulling the joint. So it's a tensile force. So we assume that it's a tension force. FBA, it's also pulling the joint B. So this is also a tension force or tensile force, right? And then in the end, if we get a positive number, it means that our assumption was correct, right? And if we get a negative number, then it means that it was not a tension force, it's a compression force. So we can put an opposite arrow to show the compression, right? Okay. So that's how we do the free body diagram, and then we just apply equations of equilibrium, sigma fx and sigma fy, to find out the unknown member forces, right? But if you look here in this case, the diagram which is already there, so they have taken this FBC as compression, right? Because just by visualizing that the forces applied, tensile forces applied at joint B, so there will be a compression in member BC, right? So if you can make out that, if you can visualize that, then you can say that it's a compression. But if not, then just take tension in all the member forces, right? Take all the member forces, assume all the member forces as tensile forces, right? Like what we have done here. Okay, so that's how you are going to do with the method of joints. Now, what are the steps for analysis, right? If the truss support reactions are not given, draw a free body diagram of the entire truss and determine the support reactions using scalar equations of equilibrium, right? So if there are no support reactions, then we need to find the support reactions, right? So draw a free body diagram of the entire truss and determine the support reactions, right? So just make sure that you are using method of joints, but to find the support reactions, you need to draw a free body diagram of the entire truss, right? Okay, so with this step, your support reactions are done. Now, what next? Draw the free body diagram of a joint with one or two unknowns. Why one or two unknowns? Because we only have two equations of equilibrium, right? Force equations, sigma fx and sigma fy. So we can only solve two unknowns, right? So if we have a joint with a, let's say with three unknowns, can we solve that? No, the answer is no, right? We can only solve a joint with two unknowns, two unknown forces, right? So there will be there will be joints in the truss which have more than 2 unknowns, right? And there will be joints where you have 1 or 2 unknowns. So start with the joints which have less number of unknowns, 1 or 2 unknowns, right? And then work your way towards those joints, right? So by the time you reach there, you will be knowing some more forces, right? So there'll be lesser unknowns left at that joint. Okay, so assume that all unknown member forces act in the tension unless you can determine by inspection or visualization that the forces are compression loads. We already talked about it in the last slide, right? So just make sure that you take tension in all the forces, unless if you really say that, okay, I can make out that this is a compression force. So then you can make it a compression force, right? Otherwise, take tension in all the member forces. Okay. Next step is apply the scalar equations of equilibrium. So now you have a free body diagram of a joint with 1 or 2 unknowns. Just apply sigma fx equals to 0 at that joint, sigma fy equals to 0 at that joint, not the whole truss, to determine the unknowns. If the answer is positive, then the assumed direction, if it's a tension, is correct. Otherwise, it is in opposite direction, or it's a compression, right? We already talked about it on the last slide, right? Okay. Repeat steps 2 and 3 at each joint until all the required forces are determined, right? So you start from one joint and then you keep solving other joints until you know all the member forces, because that's the result which you want, right? Because after you know all the forces, then the analysis is done. Okay, so these are the steps which you need to follow for the force analysis of a truss system by method of joints, right? So now let's talk about zero force members. This is section 6.3 of your book. What is a zero force member? With the name, it suggests that any member of the truss which has a zero force, zero internal force, right? Or zero member force. So they are called zero force members. Now, how can you identify, how can you make out, how can you determine that, okay, this is a zero force member, right? So there are 2 different conditions. Let's talk about the first condition. If a joint has only 2 non-collinear members and there's no external load or support reaction at that joint, then those 2 members are zero force members. Now, this is the truss, which is being shown on the left side, right? So in this truss, now if you consider this joint D, at joint D, you have 2 members, DC and DE, right? So these 2 members are non-collinear, right? Non-collinear, and at joint D, there's no other member, and there's no other external load, and there's no other support reaction, right? So with that, we can say, okay, this member DE and member DC are zero force members, right? So that's the condition. I mean, if these conditions are fulfilled, then we get zero force members. And what's the benefit of getting zero force members? Let's simplify the analysis, right? So it makes the analysis easier. Again, if you look at here at this joint A, then we have 2 members, AF and AB, right? And there's no third member. Both of these members are non-collinear. There's no external load. There's no support reaction at point A or joint A, right? So member AF and member AB are zero force members, right? So we need to see that. We need to take into account of this important information, because once we are solving the problems, the truss problems, so if you can make out that, okay, these 2 or 3 or 4 or even 1 zero force member, then it simplifies your analysis, right? Okay. Now that was the first condition, right? So now we'll have a look at the second condition. Before that, we can just say that zero force members can be removed as shown in the figure when analyzing the truss. So this bottom figure is the same truss which is at the top, but we have taken out this member CD, member DE, member AB, and member AF, right? So for force analysis, you can take off the zero force members and then you can analyze the truss, right? Because they are zero force members, so they don't really mean anything in the truss, right? But they are there for stability, right? Okay, so let's move forward. Let's see the second condition, right? So first condition was two members, non-collinear, no external load at that joint, no support reaction on that joint, right? Now, if there are three members at a joint, then if two of the members are collinear and there's no external load or reaction at that joint, then the third non-collinear member is a zero force member, right? So if you understand that, let's take a look at this figure on the left side. So we have this truss, this simple truss, where we have different joints. Now, if you want to have a look at joint C, so there are three members which are jointed at joint C, right? Member CB, CD, and CA. Now, if you look closely at joint C, so two of the members, CB and CD, are collinear. And the third member, CA, is non-collinear, right? So then member CA is a zero force member, right? Now, if you look at joint D, we have three members, of which two members, DE and DC, are collinear. And member DA is non-collinear, right? So the non-collinear member at that joint is a zero force member, right? So, so we can also remove the zero force members. Okay, we already saw that. And just to repeat, on the left bottom, we can see the figure that we have removed the member AD and member AC from the truss, and which simplifies the analysis, right? So no need to find out the member forces in CA and DA, because just by looking at the truss, we can make out that, oh, these are zero force members. So we can just remove those members. And why these zero force members are there? They are used to increase the stability and rigidity of the truss and to provide support for various different loading conditions. So that's why we use zero force members in the truss. Okay, so after we are done with this, let's go over an example of the method of joints, right? So there's a truss which is shown on the left side of the screen with 1, 2, 3, 4, 5 members and 1, 2, 3, 4, 4 joints, right? So there's a simple truss, there's a planar truss. Loads are as shown on the truss, and we need to find the forces in each member of the truss, right? So the dimensions are given. We have 450 pounds load at joint D at the top, and we have two supports at joint A and joint C, right? And we need to find the forces in each member of the truss. Okay, so how should we go about this problem? Let's talk about that. So first, as we already saw, that what we need to do, we need to know that if there is a zero force member or not. Okay, so let's check if there's a zero force member or not. So if you just take a look, just visualize this truss, just see that do we have a zero force member, right? So as you can see that member BD is a zero force member. Why? Because if you just take a look at joint B, so it has 3 members jointed together at joint B, right? Out of which member BA and BC are collinear, and only member BD is non-collinear to these members. And there's no other external force, external load, or support reaction at joint B. So member BD is a zero force member, right? So we can just write at the start that BD is a zero force member and FBD equals to 0, right? So that's the first thing we can do. So after making out that we have a zero force member and we already got 1 member force done, so then we can analyze joint by joint, right? So then we can start, let's say, from joint D, and then we can solve joint A, right? Why not from joint A? Why not we can start from joint A? That's a good question, right? But why? Let's see. If we start from joint A, how many unknowns do we have? We have member AB, member AD, and we have 2 support reactions. Or this is a rotor support, so we have 1 support reaction at joint A. So we have 3 unknowns, 3 unknown forces at joint A. But we have only 2 equations, sigma fx and sigma fy. So can we solve joint A? No, the answer is no, right? So let's start from joint D, because we only have 2 unknown forces, DC and DA, because we already know that DB is out. It's a zero member force, right? Zero force member. Okay, so let's start from joint D. Now, again, just how to make the free body diagram. Let's do that again. This is joint D, right? So let's first put the external force, external applied load. This is 450 pounds load, right? Then you have this guy here and this guy here. As I said, that you should take tensile force in all the assumed forces, right? And unless if you can make out that okay, it's a compression force, but take tensile force in everything. So FCD and FAD, these are the 2 unknowns at joint D, right? So this is your free body diagram, and you can make out that this is 45 degrees. This is also 45 degrees. Okay, so this is the free body diagram of point D, joint D. Now, just apply sigma fx equals to 0 and sigma fy equals to 0 with the sign convention as shown. And let's talk about sigma fx first. So if you take sigma fx equals to 0, then you have 3 components, 3 forces. 450 pounds force, which is a negative because it's going in the negative x direction. And then you have FAD, the x component of FAD or FAD cosine of 45, this guy, which is again negative because it's going in negative x direction. And then you have FCD times cosine of 45, the x component of FCD, and this is going towards the right side. So it's a positive force, right? So this guy is positive force, and that's all we have. We only have 3 forces in x direction, right? Equals to 0. Now, if you go for sigma fy, so you do sigma fy, how many forces do we have in y direction? we only have y components of FAD and FCD, right? So just take that, both are acting downwards, so both are negative. So negative FCD times sine of 45 and negative FAD times sine of 45 equals to 0. Right? So these are the two equations, and from here, if you just solve these equations, you get FCD equals to 318 pounds. We get a positive number, so it's a tension, as we assume tension, and we got a positive number. So we say, okay, it is tension. And FAD, which is negative 318 pounds. So this negative sign suggests that we assume tension, but it's not tension, it's a compression, right? So we'll change the arrow for FAD, right? It's not a tension, it's a compression. Okay, so now after doing this, what do we know? Now we know this guy, we know this guy, right? So now we can analyze spin A, right? Because now we have less number of unknowns because we already know FAD, so we only need FAB and AY, right? So let's draw the free body diagram of joint A. So this is your joint A. Now AY, we know that it should be upward, so let's take AY in upward direction, and then FAB and FAD as tensile forces, right? And FAD, we already know what is FAD, right? FAD is negative 318 pounds. So it's a compression. Okay, so either you take FAD as negative 318, or you put a compression sign on FAD. So this is one option where you can take the FAD as negative 318 pounds and put the tensile sign, right? Tensile arrow. Or you can say that, okay, this is joint A. Now, this is your AY. This is your FAB. And this is, because we already found out that FAD is a compression force with a magnitude of 318 pounds. So we can say that this is 318 pounds, right? And a compression. Because now it's pushing the joint, so it's a compression. So either one is correct. This is also good. This is also good. We'll get the same answers, right? So now, for now, let's go ahead with this. Okay. So FBD of point A we are already done. Now just apply equations of equilibrium. Sigma fx equals to 0 and sigma fy equals to 0. All right. So with the sign convention of rightward positive, let's do sigma fx, which equals FAB and the horizontal component of 318 pounds. So negative 318 cosine of 45. Okay, so that's the equation for sigma fx, and from here you get this guy FAB, which is 225 pounds. It's a positive force, which means that our assumption is correct, and it is a tensile force, right? Okay, and with this, we are done with the problem 1 of this truss, because now we know this, this is a zero force member, right? And because this is a zero force member, so FAB equals FBC, right? So we can also say that FAB equals FBC. Because if you consider joint B, this joint, then there are only two forces, FAB and FBC, because FBD is a zero force member, right? So then FAB and FBC should be equal, right? So to have equilibrium at joint B, right? So we can just write that to have equilibrium joint B, we should have this guy, FAB equals FAC, right? So that's how we are done with all the member forces, and we are done with the force analysis of this truss. Okay, let's quickly go over to the example 2. Now this is another, simple truss. The loads are as shown. We have 600 newtons and 900 newtons, two external forces, and we need to determine the forces in all the truss members, right? And we need to make sure that we write whether it's a tension or a compression. So this part is really important. You need to show in your answers that if it's a tension or a compression. Okay, now how we go about this? Check if there are any zero force members. Okay, so we need to find out if there's a zero force member. Draw free body diagrams of pins D, C, and E, and then apply equations of equilibrium at those pins to solve for the unknowns. Okay, we already know these steps, right? Okay, now let's talk about the free body diagram of point D, right? Now again, why point D? Because we have only two unknown forces at joint D, right? So let's take joint D so that we can solve joint D, right? Okay. So before that, there was one question here: is member CE a zero force member, right? So let's look here. Let's look at this diagram. What about member CE? Let's take a look at joint C. We have three members, okay? Two members are collinear, CD and CB, while CE is a non-collinear member, okay? All these are fulfilled, but we have an external force, external load at joint C, 900 newtons, right? So that's why CE is not a zero force member, right? So we need to make sure that all the conditions are fulfilled to make any of the member zero force member. So now coming back, let's start from the free body diagram of joint D, and this is the free body diagram. Let's say this is joint D, right? And so we have 600 newtons force acting in negative x direction. Let's put that here, this guy, 600 newtons force. Then we have two member forces, FDE and FDC. Now FCD, they have taken in the tensile direction, but FDE, they have taken in the compressive direction, right? Due to this load, 600 newtons load, right? Because if you visualize that if 600 Newton force is coming on to this joint D, then it's giving compression to member DE, right? So if you are giving compression, then you can assume that, okay, member FDE is in compression, right? Okay, so for now, just go with this idea that FDE is in compression and FCD is in tension, right? Okay, and we have this 3, 4, 5. We can make out that this is 3, 4, 5 is the triangular ratio, right? Okay, so Now you can just do sigma fx and sigma fy and find out the forces. So if you do sigma fx, what do you have? FDE, the x component is 3 by 5, so FDE times 3 by 5 minus 600, because 600 is the x component, right? So if you do that, you get FDE, which is 1000 newtons. So 1000 Newton, or it's a compression, right? So we assume that it's a compression and we got a positive number. So this is confirmed that this is a compression force. Now let's do sigma Fy. If you do sigma Fy, how many forces do you have, right? So you have FCD and then you have a Y component of FDE. So you will get 1000 times 4 by 5 negative FCD, because FCD is acting downwards, equals to 0. From here you get FCD equals 800 newtons, this guy. So we assume tension and we got a positive number, so that means that this is a tension force. Okay, so that's how we are done with joint D, and we were able to solve for this member and this member. But we still have more members, right? So let's go to joint C. Why joint C? Because there were 3 unknowns at joint C, right? But we are already done with this member CD. So we are left with 2 member forces, 2 unknown member forces, so which we can solve, right? Okay, so let's make the free body diagram of joint C, and how many forces do we have at joint C, right? So we have an external force of 900 newtons acting in the negative x direction as shown in the blue arrow, and then we have 3 member forces, FBC, FCE, and FCD, out of which FCD is already known from the last step, and FBC and FCE are the 2 unknown forces, right? So that's how we're going to analyze this joint C. And now here, FBC is taken as a tensile force, while FCE is again, because of the applied load at joint C, is taken as a compression force. But again, you can assume FCE also as a tensile force, right? And in the end, if you get a negative number, then you can make it a compression force. So that's up to you. That's up to your analysis, right? Okay, so we are done with the free body diagram. Now you can just analyze joint C, and if you do sigma fx equals to 0, you get FCE, and you get negative 900, because FCE is acting in the right direction, positive x, so it's a positive force. 900 is acting in negative x direction, so it's a negative 900. So you get FCE equals 900 newtons, right? So FCE was assumed as compression. We got a positive number, which means that it's a compression force, right? So that's how you are done with this. Then if you take sigma Fy equals to 0, there are 2 forces, the 800 newtons FCD, which is a tension force. So it's a positive 800, and FBC, which is acting downwards. So we have a negative FBC here. This guy equals to 0. And from here, you get FBC equals 800 newtons. Right? So we already knew this and this. Now we are done with FBC and FCE. Okay, so how many member forces we are left with? We are left with 2 member forces, right? So now let's solve point E, joint E. Joint E, and for joint E, we already know this, right? So if we only want to find out FEA and FBE, right? Okay. So the free body diagram of joint E, we have 1, 2, 3, 4 forces which are acting at joint E, but out of these, we already know two of the forces, FDE and FCE, right? So we are only left with two unknowns. So we can just apply two equations of equilibrium and we can find two unknowns, right? So analyzing joint E, let's write the equations of equilibrium. Let's write down sigma fx equals to 0. We have 4x forces on this joint, which are FAE times 3 by 5, which is the triangle ratio, plus FBE times 3 by 5, again the x component of FBE, and negative 1000 times 3 by 5, which is the x component of FDE, and negative 900, which is the applied force in x direction, right, equals to 0. Okay, so this is the first equation which we get, and then if you do sigma Fy equals to 0, then you have three y components of acting at this joint, right? And you sum them up and put them equals to 0, and then just solve these two equations, because these are two equations and there are two unknowns, FAE and FBE. So we get FAE equals 1750 newtons. And FAE was already assumed as compression, and we get a positive number, so which means that this guy is a compression, right? And FBE, we get 750 newtons, this guy. So FBE was assumed as tension, we got a positive number, and which means that it is a positive force, it's a tensile force, right? So now we are done with this, FAE and FBE, right? So with this, we are done with everything. We are done with the whole analysis of this truss. So that's how we are done with these two problems, and that's how we do these kind of problems of truss analysis with method of joints, right? All right, guys. So thank you so much for watching, and we'll see you in the next lecture. Thank you.